share your screen, and floor is yours. Please go ahead. Before we start, we have right now plenty of time, but let's follow some kind of schedule, and I suggest 15 minutes for presentation itself, and just to keep some time slot for question, because it's a good sometimes to ask question, like get some feedback, right? So Igor, would you please just 15 minutes for your presentation would be enough? I guess it would be enough for you.
I will try.
Please go ahead.
Dear colleagues, dear organizers and participants of conference report, Structural-Parametric Synthesis of Multy-Agent UAV-based SMR monitoring system and Ontology approach. A report includes 3 parts: introduction, where presented motivation, state of the art, aim of this work, and objective of research. Main result with ontology model, an approach of ontology model utilization for synthesis structure monitoring system, and an example of research with approach to utilization with ontology, and conclusion. Nowadays, the use of SMR is considered as the main direction for increasing power generation capacities, replacing outdated capacities, and generating electricity in hard-to-reach regions. SMRs are recognized as objects of increased dangers, and high safety and security requirements are imposed on them. Unmanned aerial vehicles are recognized as a flexible tool to use of which provide to improve the safety and security. Oh, I'm sorry, I forget switch on my camera. There are general approaches of unmanned aerial vehicle utilization that targeted on this aim. Inspection and monitoring components of SMR, deploying ad hoc networks in case of damage in wired communication, utilizing UAV as part of physical protection system, and deploying UAVs to quickly assess the area involved in the emergency and provide situation awareness. For instance, UAV can be used for surveying and mapping the terrain of SMR site area and enroute this area to evaluate accident consequence. In this case, of course. There are 2 modes to define ways for utilizing multi-agent UAV-based SMR monitoring system: normal and post-accident. The main specialty of utilizing UAV in post-accident modes is performing tasks as a resource system in case of damaged mine system, for instance, deploying wireless connection in case of damaged wireless one. The task of monitoring, inspecting security and emergency response for SMRs belong to the task of covering area or covering points when UAV equipped with cameras, sensors, and other instruments can be utilized to perform routine inspection and monitoring of SMR's components and SMR site area. And deploying flying wireless network are related to the task of point coverage, when UAV can carry equipment to perform collecting or transmitting data from SMRs or monitoring stations to the SMR's control room or center. When performing this task, it's necessary to take into account the size of the SMR site, specification of UAV and their payloads, requirements for frequency of information update, durations, and dependable of mission, and conditions, day or nights, simple, complex weather conditions. A variety of tasks, and certainly even the variability of conditions for their implementation determined the use of a multi-agent approach when creating monitoring system. The information model of multi-agent system uses ontology that allows describing the composition, state, and interaction between the components and of this multi-agent system. Approaches to the synthesis of complex system, including the use of ontologies, are considered in many works. Juma et al. Propose an approach to developing a UAV-based monitoring system with detector comparison for Arduino sensor model. Paper Ontology-based system engineering presents a comprehensive summary of the state-of-the-art of ontology-based system engineering, as well as illumination a roadmap for future directions. The approach to the development of computer system for automated construction is presented in paper formation of efficient pipeline orientation operation procedure based on ontological approach, and general algorithm to justify the structure and composition of UAV-based monitoring system, considering the requirements and limitation of missions, are described in work UAV fleet-based accident monitoring system with automatic battery replacement station. Most of the considered studies suggest approaches of ontology utilizations for only the backbones of complex system, but do not consider how to use this ontology for synthesis structure with system to perform specific tasks in real condition. And the paper consider the use of ontology as the basis for the structural parametric synthesis of the multi-agent UAV-based SMR monitoring system, which allows perform various missions, taking into account the real conditions and the requirements for these missions. And the result of the use ontology in this case are type of unmanned aerial vehicles and payload it's necessary to perform specific task, and the necessary composition of UAV support system. Because in case to deploy long time mission and restriction on the flight endurance of UAV, necessary to support this mission with specific aerial or, for example, ground automatic battery replacement station. The objective of research are follow: developing an ontological model with classes, individuals, and relations, developing an approach of utilization ontology for a multi-agent UAV-based SMR monitoring system, structural parametric synthesis, and research and approach of utilization ontology on short use case. Situational creation of a structure of complex system for specific tasks can be taken care of for a large number of different solutions in specific object area. A formalization way of such knowledges is the development of ontology. There are top-level ontology, which define a general fundamental description of a field of application, subject field ontology, and application level ontology, low level. The multi-agent UAV-based SMR monitoring system ontological model describe the structure and relation of next elements or classes. Next classes used in the ontology: mission type, inspection and monitoring, deploying ad hoc networks, security, and emergency response with two sub-missions: dual rate measurements and radiation source locations. Mode: normal and post-accident, performing unit simple UAV and custom UAV, which will be necessary to generate specific set of sensors to perform specific mission. And support unit, this is automatic battery maintenance stations, and payloads: camera, FLIR, radiation dosimeter, and network equipment. In the environment conditions for with not very complex example, day and night. The list of classes and subclasses can be expanded depending on the feature of a monitoring system. And description of the object properties defined in the ontology is presented on in table 1. If individuals are added to the ontology, then data properties will be used to describe them. For example, a UAV is described by such data type properties as flight duration, maximum permission with speed, wind speed, payload, data transmission protocol, and so on. And this ontology was created with Protege software and ontograph of development domain ontology for multi-agent UAV-based SMR's monitoring system shown in figure 3. The use of the ontology to form the composition of UAV groups is carried out by transforming the mission task into SPARQL query. The result of this request is a list of UAVs with a payload and automatic battery maintenance stations for the specified UAV if it necessary. If it's necessary to add data and knowledges to the ontology, several rules are used. The place of ontology in the process of structural-parametric synthesis of this monitoring system is shown on figure 4. Let's consider the use of ontology for selection of UAVs and the equipment necessary to perform a task at least 0.8 hours at night with wind speed more than 10 meters per hour. To clarify the ontology, were added individuals to a simple UAV class, automatic battery maintenance stations, and payload class. And OL codes were added individuals of simple UAV class shown in figure 5, for individuals of simple UAV payloads shown in figure 6, and automatic battery maintenance stations shown in figure 5. And to determination the components of a monitoring system, the mission task and the requirements are transformed into a SPARQL query to the ontology as mission task transform into a specific SPARQL query, and with SPARQL query we targeted to this ontology. And as a result of this SPARQL query, a list of payloads which are used when performing a mission in night conditions, UAVs that have such payloads and can fly at the wind speed of more than 10 meters per seconds, and the list of automatic battery maintenance stations in case of it is necessary to serve UAVs with shorter flight endurance is formed 0.8 hours. And the result of this SPARQL query are presented in table 2. Given the specifics of the task, which is required, we use FLIR in the ontology, whereas only the individuals of a simple UAV class, simple UAV 2, which has FLIR and can fly at wind speed of more than 10 meters per second. Individual simple UAV 2 has a flight time only 0.65 hours, which is less than the time specified for completing the task, 0.8 hours. Wherefore, the involvement of automatic battery maintenance stations is necessary due to uncertainty of which automatic battery maintenance station can serve with UAV. 3 results are returned with a combination of all automatic battery maintenance stations class individuals. automatic battery maintenance stations 1, 2, and 3. And as additional parameter, we can use optional query or optional request in this query, for example, protocol, which can use with UAVs. And conclusion, the ontology model of a multi-agent UAV-based monitoring system for SMRs monitoring with classes and properties is developed and explored. The utilization of ontology make it possible to provide the structural parametric synthesis of multi-agent UAVs, SMRs monitoring system, and short example of use with ontology with structural parametric synthesis for inspecting and monitoring components of SMRs is given and presented. This is demonstrated what ontology alloys providing a synthesis of a multi-agent system for specific mission requirements and limitations by Sparkle query. But the most exact result requires the more full ontology description, and the next research steps can cover the development of SVRL rules for the automation implementations of new knowledge into ontology. Thank you for your attention. If you have any questions, feel free to ask right now.
Yeah, thanks, Igor, for your presentation. That's a very interesting topic. We definitely have a question right now. Colleagues, do you have any question? Okay, Tatiana, please go ahead.
Yes, thank you. Interesting report about flight of group drones, as I understood. With the interesting topic, because we have this investigation too, but I have a question about group of drones. This is the autonomous flight or control from remote pilot, or autonomous flight of group. No multi-agent, this is a drones, this is autonomous flight.
Now I work on holonic multi-agent system. In this case, for each task which can perform with multi-agent system, we used group of unmanned aerial vehicle which perform specific task, and we perform this task with collaboration.
Perform task, but in control from pilot, remote pilot, from operator, from ground, or autonomous flight?
Autonomous flight.
Autonomous flight, understood. Configuration of group. You have configurations, different configurations for monitoring, or constant configuration?
No, it's flexible approach, because we don't know how we'll change it, for example, environment conditions or conditions on the target area. In this case, maybe it is necessary to edit some UAV or automatic battery maintenance stations to perform these missions with requirements for with missions.
Yes, understood. Connection between drones, what navigation, or no, how we obtain connection?
Connection between with UAVs in group. Now I think use mesh net, where each UAV we can consider as an independent node, and in this case, I realize it's necessary to rebuild configuration of connection when this group moved our some territories. But in this case, with more flexible approach, which make it possible exchange information between each UAVs in group, each agent.
Yes, interesting, because we perform a flight of group of drones using graph theory, and you perform using ontology. Interesting approach. And control from one central drone in this group. We choose one drone, central drone, and control from this drone on other drones. No, this is our approach. Will be tomorrow our report about control group of drones in flight. Interesting, thank you. Interesting approach.
Thank you for your question.
Okay, colleagues, any other comments, question about that, about presentation? If not, Igor, I have one question for you. You mentioned like dependability of the mission and the input data for develop your ontology. Could you give me some kind of details how you incorporated the dependability of the mission in the ontology itself? Could you comment on
that? It's a complex question.
Because no, you can make very simple comments about it.
I developed a set of model which cover different strategies of utilization group of unmanned aerial vehicles to perform different tasks, to cover points, to cover area, and as indicator for in this model, I use probability of successful plan fulfillment for this group, and independent on requirements for level or for range of this probability, it's necessary different amount of UAVs and automatic battery maintenance stations structure with monitoring group, and especially required to perform specific mission planning to cover, to divide that target area into segments and use different group of unmanned aerial vehicles in each segment. And in this case, for different requirements in each case, for the probability of successful plan fulfillment, it's necessary different structure, different amount of unmanned aerial vehicles in monitoring system, and different amount of automatic battery maintenance stations, and place with support system on the target area.
Okay, I understand. So it's a dependability. It's mostly about like probability you fulfill some kind of mission, right? It's about that mostly.
Yes.
Okay, so
exactly.
Colleagues, if you don't have any other comments, question, we can thanks Igor.
Yes, I have one.
Okay, Igor, Sergey, please go ahead.
I would like to ask you about the application of this ontological model to control the specific parameters of the small modular reactors. What the parameters you are controlled, and in your presentation, I understand that your approach can be applied in the same manner for difference in other industrial production that occupied some area and need to control the environment around the danger point of production. Thank you.
Thank you for your question. Independent on task, for example, deployment sensor networks. In this case, monitoring system used only as a network to translate informations from measuring stations to a control room. And in this case, we use only follow of information, which we receive from measuring stations, for example, with Wi-Fi technology, and translate through this network, ad hoc network, to control room. Next task, for example, use unmanned aerial vehicles to search damages. For example, containments monitoring and structure of building monitoring to find damages or in physical protection system. We can perform task to translate video through ad hoc networks from this target area where SMRs deployed to a control room. And I don't concern specific parameters which can necessary monitoring.
It means that after SMR in your name of the report and in the ontological model where you remark the SMR, it is necessary to write the comma and continue for not only SMR and any industry factories, plants and chemical production and any type of micro reactors or big reactors, the similar model can be used.
Yes, I agree with you, but now we perform specific task which connected with SMRs. And I can describe how we can use this tool, flexible tool, to safety and security of SMRs.
Oh, and the same security for chemical production and so on. I talked about it.
I agree. Absolutely agree.
Thank you.
Thank you for your question.
Okay, right. We can, Igor, thanks for your presentation. We can invite the next speaker. Dmitry Maevsky,